Welcome back. So, yesterday we were discussing the monotone convergence theorem, and we also explicitly approximated measurable function g from below using simple functions, and wrote down a limiting expression for the integral of some g d mu, right. So, we gave an explicit expression rather than a supremum definition that we gave later earlier. So, in some developments this the approximation that I gave and the limit of it is taken as the definition of the integral of a non-negative function, right. This is, you can also define it that way and prove linearity becomes very easy, for example. But if you define it using the approximation I made, some other properties become hard to prove. So, the supremum definition makes certain properties easy to prove, but linearity difficult to prove. But if you take the explicit definition using this limit in the previous class, there are certain other properties that become difficult to prove, and linearity becomes easy to prove. So, they are both equivalent ways of developing the abstract integral. Now, we will talk about expectations of a discrete random variable, then we will discuss expectations, computing expectations over different spaces, and then we will derive a formula for expectation of continuous random variables. Okay. Suppose x is a discrete random variable, so, and it will take only countable values, right. So, taking values, let us say a1, a2 dot dot dot, could be finite or countable, countably infinite. So, what this discrete random variable does, so you have all these discrete values that it takes. If you look at all those omegas that map to a certain a I, let us say a 1, so that will be some set of omegas, right, and similarly a 2 will have some other set of omegas and so on. So, what a discrete random variable does is that it partitions the sample space into a, so it partitions into a countable set of events, right. So, for corresponding to each of the values it takes, its pre-image, let us call that capital A I, is an event clearly, and the omega gets partitioned by these A I's, right. So, in fact, a discrete random variable can be written as a countable sum of weighted indicators like so, I equals 1 through infinity, right. So, this could be a, if it is a finite, so if the random variable takes a finite set of values, then it is a simple random variable, right. If it takes a countably infinite set of values, then the sum the sum is an infinite sum, all right. For the sake of let's say that x is non-negative to first derive an expression for non-negative, the expectation of a non-negative discrete random variable. Okay. So, these a i's will be non-negative, and these big a i's are those omegas which map to little a I, okay, and these big a i's partition omega. Okay. Now, the task is to compute expectation of x, all right. See, if this were a simple random variable, we already know what it is. It is simply sum over I equals 1 through n a I probability of a I, right, that is from the definition. Now, this is an infinite sum, so we have to be a little more careful, right. So, what we will do is we will use monotone convergence theorem to derive an expression for the expectation of x. Okay. So, let x n of omega equals sum I equals 1 through n a I indicator a I. So, here what I am doing is only keeping so I am only keeping the first n terms, okay, and this x n of, and this is a sequence. I am going to define this for n greater than or equal to 1. So, this is a sequence of random variables and this is a sequence of simple random variables clearly, right, and I know how to compute the expectation of this, right, and it is also easy to show that x n of omega is less than or equal to x of omega and x n of omega is monotonically increasing. So, I am trying to construct a, I am trying to approximate from below the discrete random variable x using simple random variables, all right, so that I can invoke the monotone convergence theorem and obtain the expression for expectation. So, let me just do that. So, this is the definition of x n. Note x n of omega is less than or equal to x n plus 1 of omega. Why is that the case? For every, this is true for every omega, right. That is because you add one more term a n plus 1, right. So, if the omega lies in one of these little AI, big AIs, then it will be equal. If it lies in a n plus 1, x n plus 1 will be equal to little a n plus 1, whereas x n will be equal to 0, correct. So, with me, so this is okay. It is a very simple argument. So, it is a monotonically increasing sequence. So, this is easy. Next, fix some omega and omega. So, we want to show that x n of omega converges to x of omega for all omega. Okay, so, I know that it is monotonically increasing, then I have to show that x n of omega converges to x of omega, then I can invoke monotone convergence theorem, right, that is what I am trying to do here. Then there exists a k such that omega belongs to a k, right, there exists k as such that I think. So, I want to say that there exists k greater than or equal to 1 such that omega belongs to a k, correct. So, I am, so this discrete random variable is partitioning the sample space into these countable AIs, right. I am ignoring measure 0 sets, right, on measure 0 sets it may map to some uncountable set or whatever, but I am ignoring the technicality for now. So, I am just saying that the random variables takes only countable set of values and the pre images are this partition, okay. So, I am looking at some omega, okay, and that omega should be, will belong to a particular a k, right, because omega has been partitioned, right. So, whichever omega you take, it will belong to some a k, correct. So, if you look at, so then if you, then x of omega for this guy will become, x of omega will be a k, right, and so what I am saying is for this omega, x of omega is equal to a k, okay. So, for all n greater than or equal to k, we have x n of omega. So, x, see if n is less than k, so k is that guy, right, k is the index that contains my little omega, my omega, and if my n is less than k, x n of omega will be 0, right, because, so I will sum only till n, okay, and my k is bigger than n. So, it will never figure in this sum, all right. So, it will be 0, but if n is bigger than or equal to k, we have x n of omega equal to what, a k, right, and n less than k, x n of omega equal to 0, correct. Thus limit n tending to infinity x n of omega equal to x of omega for all omega. Agreed? So, x n of omega will be equal to a k for all n bigger than or equal to k, correct, and x of omega is anyway equal to a k. So, x n of omega will converge to x of omega, and this is true for every omega, right, because I fixed an arbitrary omega and proved this, correct. This is clear, sequence of arguments clear. So, I fix any omega at all and that omega must belong to some capital A k, okay, then my x of omega will be little a k, agreed. Now, if you look at x n for that omega, it will be 0 for n less than k and a k for n greater than or equal to k, which means as n tending to infinity x n of omega will converge to x of omega, and this is true for all omega, correct. So, now I have proven that x n is a simple is a sequence of simple random variables which converge to x monotonically, correct. So, by MCT I can invoke MCT, expectation of x equal to limit n tending to infinity expectation of, so expectation of x n, correct. Agreed. Now, what is expectation of x n? Expectation of x n I know because x n's are simple, right. So, this is equal to limit n tending to infinity sum over I equals 1 through n a I times probability of big A I, right, which is simply the same as yeah. So, let me just write this as probability of big A I, then this is equal to sum over I equals 1 through infinity A I probability of x is equal to A I, right. I am skipping one step. So, this limit of this infinite sum always exists because these a i's are non negative, okay. Otherwise, the sum may not be well defined, right. So, I have assumed which is why I have assumed that x is a non negative random variable to begin with, right. So, I have so this sum will always converge, right. It may go to plus infinity, but this is well defined, right. It may either be converging to a real number or it may go to plus infinity, but in either case this limit is well defined. So, which is denoted by this infinite summation, and after all capital A I is nothing but the set of all omegas for which x is equal to a I, little a I, right, and that is nothing but your PMF, right. So, you can, if you want, you can write that as I equals 1 through infinity a I p x of little a I, right. Is that clear? But that is only for non negative discrete random variables. If you have a discrete random variable which possibly takes negative values, what would you do? Decompose it into x plus and x minus, right. If x is a discrete random variable possibly taking negative values, write x is equal to x plus minus x minus, where x plus is equal to max of x comma 0, isn't it? Max, I mean max, isn't it? Max of x comma 0 and x minus is equal to minus min of x comma 0, right. So, these are the positive and negative components of this is like f plus and f minus for functions, right. I am just writing it x plus as x minus for random variables. Okay. Now, these are both, so x plus and x minus are both non negative random variables, correct, which is why I put a minus sign here. So, to make it non negative, right. Min of x comma 0 will be possibly negative, right. So, which is why I made it non negative. Define expectation of x. So, this is like, I mean, this we have already done, right. Expectation of x is equal to expectation of x plus minus expectation of x minus, which is well defined as long as we do not have a so as long as we do not have infinity minus infinity. What I really mean is, if at least one of them is finite, this is well defined. If they are both equal to infinity, then the expectation of the random variable is not defined. Okay. For a random variable that takes, well, for a random variable that takes only non negative values, it is always defined, right. This is always perfectly well defined. It might be plus infinity, but it is still well defined. Okay. But for a random variable that takes both positive and negative values, this guy may be infinity, this guy may be real, in which case the expectation is infinity. This may be infinity, this may be real, in which case the expectation is minus infinity. If they are both real, no problem, right. And if they are both infinity, the expectation of the random variable is undefined, does not exist. Okay. So, I want to make sure, so the expectation is not defined is different from saying expectation is infinity. Okay. They are both different. Expectation being infinity is well defined. Okay. Expectation being infinity is just this summation diverging to infinity plus infinity, right. Okay. So, with me so far. So, examples. So, let us compute the mean of a geometric random variable. One minus p power I minus 1 p, and this is for I greater than or equal to 1, right. So, this is geometric random variable. So, if you want to compute, so this is a non negative random variable, right. So, you can directly apply this formula, correct. So, expectation of x will be sum over I equals 1 through infinity I times 1 minus p to the I minus 1 times p, right. So, this is, so if you pull this p out, you will have an arithmetic geometric series which you can sum, right. So, what you will get is this will become p over 1 minus, so I think you will get something like this 1 minus p the whole squared, I think, Okay, I think this is what you get, right. So, if you have to sum this arithmetic geometric series, so you will get, so that will become 1 over p. Okay, just do the summation. Okay, so this step, just do it right. So this will be 1 over p. So x is the, so recall that x is the number of coin tosses before you see the first head, right. If p is the probability of head, x denotes the number of coin tosses before you see the first head, right, and the expected number of those coin tosses is 1 over the probability of head, which makes sense, right. So if the probability of head is 1 in 3, the expected number of trials before you see a heads is 3 is what this is saying, right, which makes sense. Yes.
If you are finding that expectation of that negative random variable as a limit of xn, limit tends to infinity expectation of xn, then you take the limit outside that expectation of x plus minus expectation of x minus, or is it limit expectation of x plus minus limit expectation of x minus?
So what you have to do to be mathematically sound, you have to express x as, first you have to express x as x plus minus x minus. So these are both non-negative random variables. For each of these random variables you approximate monotonically. Yeah, you compute, so which is why I am writing it like this, right. You have to compute the positive part separately and negative part separately, and for the expectation of x plus you will compute using this formula, expectation of x minus you will compute using a similar formula, and then you subtract one from the other if the subtraction is well defined. If it is both infinity, it is not well defined.
So if x plus and x minus are like x is symmetric over x axis, x plus and x minus will be basically equal, minus x minus will be basically equal.
We will get to that example. We will see an example like that. So this is okay. This is a very simple example. So I want to, so this is a case, this is a very benign case where it's a non-negative random variable and the summation worked out to be something finite, right. So the mean is, the expectation is 1 over p, right. Now we will give an example of a case where the expectation is plus infinity. So if you, I think I put this down before, let probability, so let me put the PMF as p of x is equal to k is our 1 over k square example, right. I think we did this earlier, 6 over pi square 1 over k square. This is for k greater than or equal to 1. So this is also a non-negative random variable, right. So you can use that formula. So in this case what you get, expectation of, so you have expectation of x is equal to sum over k equals 1 through infinity, k times probability of x is equal to k, right, which is equal to 6 over pi squared sum over k equals 1 through infinity, k times 1 over k squared, right, which is 1 over k, and this is harmonic series, right. So this diverges to plus infinity. So this is equal to plus infinity. So this here is an example of a random variable with mean is equal to infinity. It is well defined, okay. It's the mean is plus infinity, the expectation of the x is plus infinity, okay. Okay. Right. Now to move on to another example, I just want to tweak this example to make it two sided, like he was mentioning. I want to give a third example where the expectation is actually not defined, okay. So, what I am going to do is this guy has 1 over k square kind of probability mass in the positive axis, right. What I am going to do is make it symmetric. Okay. So, let consider this example. Let probability of x is equal to k equal to now 3 over pi squared 1 over k squared for k in all integers, but not 0. Okay. So, essentially this is a PMF defined over plus or minus 1 plus or minus 2 plus or minus 3 and so on. Okay. It is defined over non-zero integers. Okay. So, in this case, so you can verify that this is a valid PMF because I mean you can, this will sum to 1, right. This is clearly a valid PMF. Now, in this case now you have to be very careful, right. You have to compute x plus and you have to compute the x plus and x minus separately, correct. So, what you do is you will have one the expectation of x plus will be plus infinity, expectation of x minus will be plus infinity, right, because you get two harmonic series, right. And in this case what will happen is, so since they are both infinity, expectation of x will not be defined, right. Expectation of x plus will have a harmonic series, expectation of x minus will also have a harmonic series, right. And therefore, it will, so expectation of, so x plus will have a PMF like that, right, like 1 over k square kind of a PMF. So, expectation of x plus will be plus infinity, expectation of x minus will also be plus infinity, therefore, expectation of x will not be defined. So, what you cannot do, so one caution I want to give you is you cannot write it like this, right. The following is wrong, what I am going to write now is wrong. Okay. So, you cannot write this as sum over k equals 1 through infinity k times 1 over k squared, forget the pi square outside. So, I will just do that for positive plus k equals 1 through infinity minus k over k square, right, and 3 over pi square outside, right. So, if you write it like that, you cannot cancel corresponding terms and say the expectation is 0, okay. That is not allowed, because whenever you have a summation which contains both positive and negative terms, right, you cannot take any grouping you like, right. I think you might have studied this in sequences in series, right. If you have summation a n, some terms are positive, some terms are negative, you can actually group these terms in any which, so you can get any answer by grouping the terms in some particular way, right. So, in particular you are not allowed to group such that the answer is 0, okay, that is not valid. You have to compute them separately and say infinity minus infinity is undefined, okay. You might have known that. So, I mean if you sum a n, summation a n, if the summation is absolutely convergent, then you can group any whichever way you want and you will get the same answer. But if it is not absolutely convergent, this is not absolutely convergent, you cannot group it any whichever way you want, okay. So, that is something you already know, I think. So, here the expectation is undefined, okay, it is not 0, okay. I want to make that clear, and it's and this is a different example from this. Here the mean is infinity, the expectation of x is plus infinity, here it is undefined, okay. They are different cases. So, this is not 0, you should not say this is 0, okay, this is wrong. So, this so if you say this is 0 is wrong, okay. Any questions so far?
So the Bernoulli random variable, the mean will happen as half, but there is no physical interpretation because 0 is success.
So if you have a Bernoulli random variable is a simple random variable actually, and in that case the mean of a Bernoulli random variable with parameter p will simply be p, right. So that is expectation of x, that's the end of it, right. So the physical so far we have not given any interpretation of expectation of x, right. We have just called it an expected value or expectation or mean or whatever, but we have not given it, simply the integral of x dp, that is all we have said, it is simply a number, right. The interpretation of the expectation is given by the law of large numbers, right. We will give it a physical interpretation, a frequency interpretation, if a frequentist interpretation when we do law of large numbers. So as far as you are concerned now, it is just a number, okay. Okay, everybody with me? Okay, so that concludes discrete random variables, expectation of discrete random variables. So I have a next I will move on to expectations over different spaces. Suppose I have a situation where, so I have a random variable x, this is my omega, this is my x, and let us say I have this is g, and so I have y equals g of x. Okay. So I have some function of a random variable which is also a random variable if g is a measurable function. So what I want to do is, let us say I want to compute the expectation of y, expectation of g of x, right. So what you have been what you would expect is that, suppose I know the probability law of x here, or I know the probability law of y here, right. I should be able to compute the expectation of y in any of these spaces and they should be equal, right. So what I am trying to say is, let us say if you have a, let us say x is discrete for the time being, just to fix ideas, if let us say x is discrete for the time being, taking values a i's. So what I want is the following. So I want expectation of y, right. So I want expectation of y, right. So expectation of y will also be a discrete random variable, right. Let us say actually let us say that it is all non negative also, to fix ideas. So I am trying to say that I want expectation of y, I want to be able to compute as yi probability that y, see this is fine, right. Let us say I equals 1 through infinity or whatever. So this is one way of computing it. Another way of computing it is to simply look at the value of g of x, right. I want to say it is equal to g of xi probability that x is equal to xi, right. So I want this to be true. So this is what I want, right. I hope this is true, rather hope, right. I say hope this is true. I equals 1 through infinity. So g of xi, probability that x is equal to xi. So, what I am saying is, so the random variable takes values x1, x2 and so on here, and it takes, after the mapping, it takes values y1 equals g of x1, y2 equals g of x2 and so on. Okay. So, this is something you have been doing in your elementary probability, right. So, if I tell you that these are the values that my y takes, and if you somehow figured out, say let us say I know the PMF of x, right, you can do your transformation of random variable stuff and figure out the PMF of y, and then you compute this. That is one way of doing it, and that is expectation of y. But you sometimes, if I am, so if suppose I ask you to compute expectation of x squared or log x or something, you also do a sum over x square probability. So, you know what, so you would do this, right. So, g of xi probability x is equal to xi. You probably have not thought to think whether they are actually they actually equal, right. You know that you get the same answer in any whichever way you do it, but you have just been doing it, I guess, in your elementary courses, right. Suppose my g of x is x squared, you would either compute the PMF of y equal to x square and compute its expectation, or you will simply put xi squared probability of x equal to xi, and you always get the same answer, right. It is, and so this is what you have been using, and this is what you hope is always true, right. So, that is the theorem we are going to prove in full generality now. Okay. So, what I am doing here is, this is expectation over this space, if you think about it, right. I am just integrating y with respect to the probability law here, and this is integrating gx with respect to the probability law here, right. I want to say that they are all equal, right. That I just wrote it down for discrete random variables, but it is true for all random variables. Okay. Understood. So, this is what I am going to prove in full generality. So, this is an important theorem. So, you have this setting. Okay. So, now you have y equal to g of x, and x is a random variable on omega f p. Okay. Now, in the setting you have integral y dp is equal to integral g dp x equal to integral y dp y. Okay, that is the theorem. Okay. So, it says it has how many statements? Well, this is the definition. So, that is not a statement. So, that and that, right. It says that these three integrals are equal, right. So, you can either compute expectation of y by just computing. So, y is the overall map, right, and obviously expectation of y is integral y dp by definition. What this theorem is saying, that you can rather integrate this function g. So, if you just forget this part and you take this function g and the measure p x sitting here, you can integrate g with respect to p x, or you can integrate the function little y with respect to the law of y. Okay. So, in the more elementary terms that I just told you, this guy is equal to this, and this guy is equal to that, right, and they are both equal to expectation of y. Okay. That is what the theorem is saying. Is the statement clear? So, you are integrating over different spaces. Here you are integrating over, here you are integrating over omega, right, there is an implicit omega here. Here you are integrating over r, and the r is this r, and here also you are integrating over r, that is this r, okay. And the measures are all different. This p x is a measure here, the law of x, and p y is the law of y, is a measure on this, okay, and this is always true. So, what you have been doing is right, okay, and it holds in much greater generality. Okay. Now, how would you prove this? There is only one way to prove anything in integration, right? Start with simple function, right? There is really no other way of doing it, right? Start with simple functions, then use either the supremum definition or monotone convergence theorem. Now, you have monotone convergence theorem to generalize for approximate any non-negative function using simple functions, right. So, I do not know if I will complete today. So, the time is, I have 5 more minutes. Let me see if I can finish this. Let G be simple. Taking values y1, y2 dot dot yn, right. So, what I am saying is that this G is a simple function and it takes only n values, okay, y1, y2, y2 yn. Then integral y dp is equal to, so this is a simple random variable. So, I know what its expectation of y is, simply I equals 1 through n little y I probability of omega for which y of omega equal to little y I, right. So, this is my big A I, if you like, the set is my big A I, right. So, this I can write as I equals 1 through n little y I probability of omega for which g of x of omega equal to little y I, right. Y of omega is nothing but g of x of omega, right. So, that is my that is that, right. So, I have just written out that. Now, for the second integral, integral g dpx. So, I am looking at this function g as a function from here to here and I am integrating with respect to the measure p x on this line, right, but g is a simple function, right, it takes values only these little y i's, is not it. So, this will be equal to sum over I equals 1 through n y I times p x of, say I am integrating with respect to p x, right. So, p x of those x's now, not omegas, right, those x's for which g of x equal to y I, right. So, good. So, that is equal to sum over I equals 1 through n y I p x of, so I can write this as p x of g inverse of y I, right, it is the same thing, right. This set is nothing but the inverse image of y I under G, right, and this is nothing but sum over I equals 1 through n y I probability of omega for which x of omega is in G inverse of y I, right. This I am again writing it out. So, I am going from measure p x to measure p, right. Now, am I done? So, this is equal to sum over I equals 1 through n little y I probability of G of x of omega. So, this is the probability of omega for which G of x of omega equal to y I, right. So, this is the same as this. So, these two are equal, right. So, we have proved it for simple functions, these integrals are equal, right. So, next what you would have to do is for any non negative function g, you have to approximate g using simple functions from below, then use monotone convergence theorem. Okay. So, I think I am out of time now. So, we will just keep this and resume next class with the more general for non simple functions. Okay.